So good afternoon or good morning, depends on which time zone you are. So welcome to the seminar series that hosted by the CLEAR Center at Wayne State University. So today it's our great honor to have Dr. Gibson from North Carolina State University give us a talk. Dr. Gibson has obtained a dual PhD degree that in both civil and environment engineering and public policy from Carnegie Mellon University. Her research focused on the interdisciplinary work about risk prediction due to environmental contamination and quantitative comparison of policy options for control environment risks. So her scholarly work has been very well nationally and internationally recognized. I just named a few of the awards here, such as RTI University Scholar, IBM Faculty Development Award, and many of the best paper presentation and report awards from various organizations such as NIEHS, Water Environment Research. So in addition to her scholarly achievements, she also holds a number of professional leaderships, such as topic editor of the Journal of Environmental Science and Technology, that is one of the top journals in our field. And I think more importantly, Dr. Gibson is our good friends to our department, Civil and Environment Engineer at Wayne State University. She has been collaborating with a few faculty in our department, and I'm also very proud to say that Dr. Gibson, it is one of our own CLEAR team members. Without further ado, I have to give to you, let's welcome Dr. Gibson to present her work about Bayesian belief networks for predicting exposure to environmental contaminants.
Thank you very much, Yang Li. Yeah, it's really nice to see you, and I'm sorry I can't be there in person. I really enjoyed my previous visits to Wayne State, so I hope I can come back.
Yes, definitely. Sometime.
Yeah. And so today what I'm really going to be presenting is results from some projects that are not the CLEAR project, but that provide some of the motivation for what I hope my team, will be contributing to the CLEAR project. And I'll talk about that at the end. So I assume most people haven't heard of Bayesian belief networks and what those are. And so I'm going to spend some time giving background on that and then show some example uses, including for one project with a similar goal to what we're trying to do for the CLEAR project. So Bayesian belief networks, are a type of machine learning method. And of course, we all know machine learning AI is really in the news. This is just a quote from a book that came out a few years ago called The Master Algorithm: How the Quest for Ultimate Learning Machine Will Remake Our World. And basically saying that machine learning is remaking science, technology, business, politics, and war. There seems to be hardly an era of human endeavor untouched by machine learning. And the same is really true in environmental engineering and civil engineering more broadly, where there's a lot of work to revisit our traditional modeling methods and see if we can improve upon them using these new machine learning technologies. And so that's an area that I've been very interested in for quite some time now. And so my hypothesis for the CLEAR project, and also for some of the work I'm going to demonstrate today, is that machine learned models can do just as well or better at predicting the basically exposure to contaminants in the environment as our traditional mechanistic models that are built based on first principles of physics, chemistry, and biology. So like I said, I'm going to spend quite a bit of time giving you some background on Bayesian belief networks to bring everybody up to speed and some of their advantages. And then I'm going to go through two examples. And one of them is a very different sort of example than that we're going to be working on for CLEAR, and the other is similar. So why might we want to, so I'll start with a little bit of why we might want to investigate Bayesian belief networks as one form of machine learning alternative to traditional modeling methods. I'll give you a little bit of background on Bayesian belief networks. And then I'm going to give you two examples, like I said, for predicting exposure to environmental contaminants. And then just talk a little bit about where, if you're interested, you can learn more. So my motivation in pursuing this work is to really, again, address some limitations of traditional methods. I'm very interested for risk analysis, which is really an area that I work in extensively. One of the most important steps is characterizing exposure. That is figuring out who is exposed to environmental contaminants at what concentrations and what locations. And so our traditional ways of doing that in environmental engineering, we really have two. Very traditional method is mechanistic modeling. And this is just a kind of schematic of a mechanistic model for, very crude schematic for predicting, say, the concentration of a contaminant at a well. Here's a receptor well. After this contaminant leaks from some sort of contaminated area into the soil and groundwater. Another approach we might use, though, and so these mechanistic models are really based on trying to do our best to replicate this process using a series of mathematical equations that represent our basic knowledge of physics, chemistry, and biology of contaminant transport. So using a mass balance model like this one, where we look at the change in mass per unit time across a control volume as a function of basically the amount of mass coming into the control volume or being generated with the amount of mass leaving the control volume, sources of mass, so sources of pollution within that volume, and then plus or minus any gain or loss of the contaminant due to chemical and biological reactions. Another approach that can be used is statistical methods, where you might take, say, a set of data. For example, these maps show data of concentrations of nitrate in well water in North Carolina, and the points are locations where concentrations have been measured either in monitoring wells on this side or in private wells on this side. And there are statistical methods for extrapolating. So if you want to know what the concentration is in an area where you haven't measured, so this is kind of a schematic zoom in of these areas, you can predict concentrations based on what's been observed around through various statistical methods. So those are kind of our two traditional approaches for exposure assessment. But there's some limitations to these approaches. So for mechanistic models, basically, these models really can require a lot of computing time. Groundwater models can be especially time intensive. For groundwater models, of course, and for any mechanistic model, we divide the area that we're interested in into a series of tiny control volumes. And then we kind of analyze what's going on within each and how mass flowing out of one control volume affects neighboring control volumes. So here's just an example schematic for an area in North Carolina that I'll be talking about, where the control volumes are basically the area is divided into this grid, very fine grid, two-dimensional grid. And then also there's a vertical grid, in this case for our work representing 3 layers. But these really do take a lot of time to set up. They take a lot of time to run. And also they rely on having knowledge of physical, chemical, and biological properties of contaminants. And that is not always available, especially for newer contaminants that, have emerged over the last few decades, or for contaminants, for example, in settings where maybe how these contaminants behave in certain geologic settings, hydrogeologic settings, is not well understood. So there's limitations. So statistical models, basically, again, this is just a schematic. We observe the concentrations at specific locations. So this is just a map showing locations where nitrate concentrations have been observed. This is from a paper by somebody else. Here's the reference. In this case, these folks were interested in whether nitrate concentrations exceeded 1 milligram per liter. And so the red dots are areas where that concentration was exceeded, and the black dots is where the concentration was measured but not exceeded. And then the question is, where else in this geographic region would we expect to see more red dots if we were to go out and take measurements? And so one way of doing that is to fit a regression model. In this case, we're looking at a 0 or 1 outcome. 1, the concentration is greater than 1, or 0, no, it's not. And so you could fit a logistic regression model where you're basically predicting the probability that at any location the sample will exceed 1 milligram per liter as a function of a bunch of predictor variables. And to develop these models, of course, you collect a data set of observations, a set of information about the kinds of predictor variables that might be of interest, like maybe the depth of the well, something about the hydrogeologic characteristics of the particular location, and so on, proximity to sources. Those can all be predictor variables. Use that data set to figure out what are the values of these coefficients. But the limitation of this approach is, oops, sorry, I'll go back there, is that you can see, this kind of assumes this linear equation form here. It's possible to develop nonlinear regression models, but challenging and very limited. Also, with these kinds of models, you can't really represent relationships between the variables on the right side of the equation. So it could be that x1 influences x2, and that in turn, the combination, depending on how you set these things, is going to have a different effect on the outcome that you're interested in. Very difficult to do that in a regression model, very limited. And you also, let's say you want to do backwards reasoning. You observe a high concentration of nitrate at this well, and you want to know, well, gee, what led to it? Is it because there's a potential source? Or do we have, a likelihood of being nearby a potential source, or is it something else? You can't do that sort of backwards reasoning. So I got, for these reasons, very interested in learning about Bayesian belief networks. Here I'm using a shorthand here, BBN, so that stands for Bayesian Belief Network. And I'm going to start and tell you a little bit about the history of those, kind of where they came from, how they work, and then talk about 2 different approaches for developing these kinds of models. So the real kind of founder of this approach is a very famous computer scientist named Judea Pearl, still on the faculty at UCLA. Back in 2012, he won the Turing Award, which is the computer science equivalent of the Nobel Prize, of course, named after Turing, who basically developed, the computing systems that cracked the Nazi code during World War II, Alan Turing. So very famous computer scientist who was kind of interested in seeing if there was a way to artificially represent human reasoning. So that's kind of the origins in computer science, and he began to really pioneer this approach back in the 1970s. So what is a Bayesian belief network? Well, basically, the formal definition is that it's a directed acyclic graph. Directed acyclic graph means a representation of variables. This is an example. Each of these circles is a variable. And it's directed because there are directed arrows from one variable to other variables in it. So every edge connecting variables needs to have a direction. And it's acyclic, meaning you can't start out at one place on the network and follow arrows and end up back there. If there are any cycles, it's not a Bayesian network in the mathematics breakdown. So this is just a kind of toy example of a Bayesian network model for predicting what might be causing a car not to start. So the thing that this is kind of most outcome of interest here is whether this car starts. And these are different variables that might be affecting whether the car starts. So just to see what kind of, using the car analogy, no pun intended here, if we look under the hood of what's this car start model, if we just kind of zoom in on this section, 3 of the variables in this model are battery power. In other words, is the battery still charged? Gas gauge, in other words, does the gas gauge say there's gas in the tank or not? And whether there actually is gas in the tank or not. So it may be that there's actually gas in the tank and the gas gauge isn't showing it. So just to see then, this is this directed acyclic graph. These are 3 of the nodes. And if you were to go underneath this, every time there's a relationship between nodes, the Bayesian network needs to have a representation of the conditional probability distributions of any nodes that are connected. So here's an example. This looks like a lot, but it's simple if you think about it. So what this is saying is this node battery power. Does the battery have any power? It's got 2 states. It can be either good, plenty of power left in the battery, or poor, the battery's out or almost out. So that's this node. This node is gas in tank, meaning the real state of the gas tank. It either really has gas or it doesn't have gas. And then this 3rd node is the gas gauge reading. And it depends on these 2 other nodes. You can see that from the arrows going into it. And what we know now from this is that if the battery is actually working in good working order, and there's actually gas in the tank, we can be sure that the gas gauge is going to say, yes, there's gas in the tank. However, if the battery is low, in poor condition, and there's actually gas in the tank, it actually turns out that 79% of the time, the gas gauge is going to give us an erroneous reading. It's going to say there's no gas when there actually is. So that's just an example. So in a Bayesian network, you need to have not only this picture, but underneath it is a set of relationships that describe probabilistically how each set of connected nodes is related to all of the other ones that are directly connected to it. And it's called Bayesian because Bayes' theorem is used to update the probabilities throughout this network based on evidence. So you can go in and set some evidence, like you could say, I know the battery power is good. And then the network will use Bayes' theorem to automatically update the likely states of all of the other variables in the network. And this is just another example. If we look at this part of the network, it's got 2 variables. This is a simple part where battery state has 2 different states. Either the battery's working or it's not. And the battery age is the battery old or new? And so Bayes' theorem basically can be used to kind of predict what the state of the battery is based on the age, or conversely predict the age of the battery based on the state of the battery. And so Bayes' theorem basically is just, it's a basic theorem from probability theory that allows you to kind of flip conditional probabilities. So this says, what's the probability that the battery state is working, given that we know the battery's old? So what if I want to know that, but what I know already is that I know that probability that the battery age is old, given that the state is working. Well, Bayes' theorem allows you, again, to go back and forth. And that's why I talked about this backwards reasoning property that Bayesian networks have. And it's really named after this philosopher, statistician, and minister, Thomas Bayes, who lived in the 18th century. And when you hear the term Bayesian, it really refers to any application that uses Bayes' theorem. And so there's many, many, many different statistical methods that use Bayes' theorem and fall under the umbrella of Bayesian statistics. But Bayesian networks are different. They're a form of machine learning, really. So a lot of people don't really understand that distinction. But just again, to show you this backwards reasoning example, here is my car model. Again, and if I were to go under the hood of this car model, I could say, I know that the car starts, so I can say, or car doesn't start. So I'm going to say 100% true, the car does not start. That's why this is green. And I can notice, I can notice what happens to the states of all the other nodes in the network. Here's just a few of them. So before I know if the car starts or not, so this is my kind of prior state, 7% chance the car is not going to start, then I can be 93% sure the engine's going to crank. Now I say, okay, the car's not starting. Well, then the engine's probably not cranking. The battery power is probably poor, even though my prior belief was that it was good. The gas gauge probably says there's no gas. It's more likely to say there's no gas and so on. So as soon as I change one variable in the network, it changes everything else. They also can predict outcomes from evidence. So again, let's say I know that my spark plugs are bad. What's the chance my car is going to start? So I enter this evidence, spark plugs are bad. Well, there's hardly any chance my car is going to start. So, so how do you create these Bayesian networks? You need a few things. One is you need to figure out which variables are connected, which ones are important, and how are they related. Number two, you need to be able to estimate the parameters, and by that I mean the statistical relationships underlying each variable. And then you need a set of algorithms to pass evidence. So in other words, if you go into the network and you put in evidence that a certain state is true, you need an algorithm to update everything else in the network. So a structure, a method for estimating these conditional probabilities, and a method for updating all of the nodes in a network once one of the nodes is changed. And so there's two ways to really create Bayesian networks. And a lot of the original work was really motivated, again, by trying to kind of break down how the human brain works and assist the human brain by dividing really complicated problems into chunks. And so those are, you can build Bayesian networks from expert understanding of how a system works, and then either a literature review of data on how elements of the system are connected, or collecting data on connections between elements of the system. What I've been mostly working on lately, though, is discovering the structure of a system from a data set that my students and I build. And I think what I'm going to do, well, I've got two examples. I was going to give you an example of each, and I'll try to keep this first one short because it's not so relevant to the CLEAR project. But this is an early example of work that I did with one of my students to build a Bayesian network from expert knowledge. And this project was really motivated by and carried out during the 2014 Ebola epidemic. And if you remember back then, there were concerns in the wastewater industry. Workers were concerned that, gee, we're taking Ebola patients from sub-Saharan Africa into the US, and are the workers at wastewater treatment plants that are receiving liquid waste from hospitals where these patients are being treated, are they at risk at all? Because CDC said that it was okay for hospitals to go ahead and flush liquid waste from these patients into the municipal sewer system without any pre-treatment. And so we got a project that was commissioned by wastewater utilities to look at what would be the risks under different hospital pre-treatment scenarios. In other words, how likely is it that wastewater workers could get sick, and how much could pre-treatment help? And so this is a case where, this is a brand new problem. You don't really have a big data set to work with on hospitals around the world that have treated Ebola patients to look and see what happened to wastewater workers that were, operating the treatment plants connected to those hospitals. And so you're stuck in this case with the expert knowledge approach. And so the first step, again, one of the things we need is an influence diagram, the directed acyclic graph. And in this case, we did this by consulting with experts in basically the management of patients at hospitals and the management of waste from hospitals and wastewater treatment operators, along with literature review. And then we specify basically all of the conditional probabilities in the network based on literature and also formal consultations with experts. And then again, we use some a software platform that already has that message passing algorithms built into it. So here is just a schematic of the influence diagram. What we were interested in is looking at the question of whether if there's virus in a patient waste, what the dose would be to a wastewater worker that might be working in the wastewater treatment plant or perhaps in the sewer system. What would their exposure dose be, and what's the probability that they would actually get sick as a function of that dose? So there were several kinds of variables that we needed to include it. We needed information about the nature of the patients in the hospital. So how many were there? What was their disease state? We needed information about the hospital characteristics and practices. For example, did they disinfect their waste at all before flushing it? How much dilution was occurring in the hospital? We needed information about the wastewater system, the temperature in that system, because that influenced survival of the virus, as well as dilution in the system. We needed to know at what point workers might be exposed and what tasks they might be involved in. And so this is a picture of the network that my student Joe Zabinski built. And this was built using a kind of software called Netica. And it's a free software for building Bayesian belief networks. So it looks a little different from networks I'm going to be showing later, but each of these rectangles is one of the variables in the network. And then what you can see in each rectangle is basically the possible values or states of these variables and the probabilities of each state before we put in, well, here we just have one piece of evidence that there's one patient in the hospital right over here. So for example, we might, want to know the temperature. So the temperature of the wastewater is one variable, and we broke this down into ranges, and this is the probability of the temperature being in each of these ranges. So for example, 28% probability it's less than 15 degrees C. And various other things we need to know. Another one we can control is whether the hospital disinfects its waste at all. Do they use bleach, quaternary ammonium compounds, no disinfection? That's just, or peracetic acid, that's the other one here. So that's just an example of how this is put together. And all of these relationships here, conditional probability distributions, and actually what's not showing here is the conditional distributions. But anyway, all of this information came from literature review and consultation with experts. And as I mentioned, some of the variables have to do with characteristics of the patient, like their disease state, severe, non-severe, how many patients. Some have to do with the hospital, for example, whether they're, how big the hospital is. Others have to do with the wastewater system, and then the others have to do with the workers. Okay. So let's see. So yeah, so in this network, if you double click on one of these, you can specify the hospital size. Otherwise, it's just uncertain. If we don't know anything at all about the hospital, based on a sample of hospitals that were treating Ebola patients, this is how kind of the size distribution of those hospitals. Here is the thing we're really interested. What's the chance the wastewater workers will get sick? And this is broken down into discrete states, the most extreme being a 1 in 10 chance, or from 1 in 10 to a certain. And down here is just the expected value. So we see when we, just our baseline assumption without entering any evidence other than we know there's one patient in the hospital, is that the chance of a worker getting sick is 5.3 times 10 to the minus 7. So very low chance. But if we put everything at kind of the most extreme state, still with one patient, but the hospital is small, well, I'll tell you more about this in a minute, but you can see the risk here increases to 8.5 times 10 to the minus 3, or 1 in 117, which starts to get to a level that would definitely be of concern. And what is this extreme state? It's the patient is severely ill, there's no hospital disinfection, temperature's cold, the wastewater worker is being exposed at a location very close to the hospital, The wastewater treatment plant essentially gets all of its waste from the hospital. The exposure route is that the worker is actually swallowing the wastewater, or swallowing wastewater droplets. All right. And let's see, what we can then do is test out what's the effect on this risk if we try different disinfection methods in advance. And we can see that disinfection of the hospital waste decreases the risk a lot. So the best was peracetic acid, decreasing the risk from 1 in 117 workers that would be exposed in this scenario to 1 in 100,000. So that's an example, again, of an expert kind of top-down approach where we figure out how do we think this system works, and we do our best to describe relationships among variables in the system. And this work was really done mostly by one of my former PhD students, Joe Zabinski, supported by one of my former postdocs, Kelsey Piper. And if you want to read that work, it's published in the journal Risk Analysis from a while ago. The second example is much more like what we hope to work on for the CLEAR project. And this is a case of training a model using data and then seeing how well it does in predicting what we observe. And so this case study is around a industrial facility in North Carolina, a Chemours chemical manufacturing facility. Everybody by now knows of PFAS, and this was a major PFAS manufacturer that in the early 2000s shifted from longer chain PFAS to short chain PFAS, in particular a type called Gen X, which was thought to be a safer substitute for kind of the older, longer chain PFOA and PFOS. And anyway, there was a big crisis in the state beginning in about 2014 when basically Gen X was discovered to be widely distributed in surface waters around the state and was discovered at very high concentrations in the drinking water supply of the city of Wilmington, which was basically downriver from this facility here. So down in Wilmington is down this way. And so then as a result, the North Carolina Department of Environmental Quality began investigating not only surface water, but also private wells in the vicinity. So all of these green spots are locations where at the time when I began, the Department of Environmental Quality had already conducted measurements for PFAS. So let's see. And so the challenge that the Department of Environmental Quality really faced is that what they were most interested in was whether wells had a level of Gen X, this is this short chain PFAS, at levels above a threshold that the state Department of Health, Division of Public Health had just established as kind of a health-based threshold. At the time, this threshold was 140 nanograms per liter. And so this map is showing basically areas where private wells that were tested had concentrations of Gen X that were above this threshold in red, yellow areas where Gen X was detected, but it was below the threshold, and green where it wasn't detected. And this was a very strange spatial pattern in that you had wells very close to, with high levels of PFAS that were close to wells with very low levels or no PFAS at all. And that the DEQ was finding that their kind of mechanistic models, initially ones they had built, were not really describing this pattern adequately. And they were just basically at the time, basic groundwater flow models with a source term here in the manufacturing facilities. And so we came in and we basically, I've worked on 2 projects now related to this data set, one an older one and one more recent work that's not yet published. The first one was just to see how well could a Bayesian belief network do in predicting Gen X concentrations. And this was the work that Javad Rustai did, who was a PhD graduate under Dr. Wager of Wayne State, a wonderful scholar. So he did this project really. And the first step was to build a data set. So all we had from the state was we had measurements of Gen X at 1,207 wells, and we knew the locations of the wells. We didn't know anything else about the wells, including how deep they were or what type of well they were. And we didn't know anything else about like the surrounding geology or proximity to other sources. And one of the arguments Camurs was making at the time was that wells that weren't down gradient of the facility likely were contaminated by sources other than the facility. And so we didn't know anything about, where there might be other sources. We had just come across a paper by Andy May at Ohio State, who had developed an air deposition model predicting basically atmospheric transport of Gen X from the Camors facility to the surrounding area, thinking that might be important. So what Javad did is he took these 1,207 well measurements. He sent a survey to the owners of all of those wells. Unfortunately, only 424 replied, but to get information about the type of the well and the depth of the well, he got estimates of air deposition, georeferenced from Andy May's model. And then he searched other public databases for every type of potential PFAS source we could think of, including airports, fire training areas, landfills, areas where wastewater had been applied, or wastewater biosolids had been applied to land, and so forth. And then he also obtained from a wide variety of sources different potentially important characteristics of the soil and groundwater, different data on land use and land cover, and basically, started with, again, this database of just measurements of Gen X in 1,207 wells, along with their locations, adding in all of this other information, including a survey, and in the end ended up with 422 potential predictive variables. So you can think of this as an Excel spreadsheet where we have 1,207 rows, and then 422 columns, one of which represents the measured Gen X concentration, and each other one represents something that maybe could be related in some way to Gen X measurements at that site. So the next question was to figure out, well, which of these things really do seem to be influencing the observed concentrations of Gen X? And that is what we wanted to do, was to learn a structure for the model. Also, not only how are these 422 variables potentially related to the Gen X concentration, but how are they related to each other? So to learn the structure of the model, that's step one. And the first thing that he did was, you can't include all 422 variables, especially when you have 1,207 observations. That's way over parameterized, and likely most of them aren't important. So the first step is to figure out which ones are important. And that is done via an approach called unsupervised learning. And basically, there are algorithms that just discover how closely related different variables are to each other. And in this case, we looked at clusters and identified clusters, key clusters of things, variables that were closely related. And then we're able to look, so it's sort of reducing the dimensionality of that data set from basically 421 columns to a much smaller number of columns that each represents a cluster of variables. And then we eliminated the clusters that didn't have any relationship to Gen X, had really no significant value in predicting the concentration of Gen X. Eliminated all those. And then with the remaining variables, sought to use various algorithms to find the structure with the best fit to the data. And the way that computer scientists measure the best fit with these kinds of models is with something called the minimum description length score. And I'll say something more about that in a moment. Then after the structure is learned, what we have to do is estimate all of those underlying conditional probability distributions. So the minimum description length, again, this is kind of the key measure that's used to decide, what network might be a good network. There's obviously an infinite number of networks. When you have all of these different variables, some of them can take an infinite number of states. You can have any sorts of relationships possible. And so we need some way to compare all the possible networks and figure out which ones might be good. And so this minimum description length score basically looks for a trade-off between how much space, how many bits do we need to store the data, and how accurately with this compressed data set can we reproduce the thing that we've observed. And just a little interesting background on this. This approach really arose again in the 70s. Those of us who grew up before the computer age remember it with the early computers. Memory was very limited. We carried around floppy disks with not very much memory. And so computer scientists then were faced with the challenge of finding the best ways to compress data. And a good way to do that is to realize that you can reproduce most of the knowledge in a data set without storing each and every variable. So that's what we're really doing here. So then the second project with this was to compare a Bayesian network model with a mechanistic, a traditional groundwater fate and transport model. And this modeling work was done through a grant we have with EPA, with RTI International. Rohit Warrior, a groundwater modeler, basically built this. And I already kind of said the basic principles of how these work. So the mechanistic model accounts for not only leakage from the Chemours facility, but also Rohit incorporated the air deposition estimates from Andy May. And then what we did is we compared the Bayesian network model alone, the fate and transport model alone, and a combined one that actually takes output from the fate and transport model and used it as input for the Bayesian network. And this is very similar to what we want to do for the CLEAR project. And then how we test the model is we use cross-validation. So what we do is we randomly divide our data set into 5 bins. We train a model, that is, we learn the structure and the parameters, or we basically calibrate a mechanistic model using these 4 training sets. Out of that, we have a model, and then we see how well the model reproduces what we've observed in the test set. And we do this over and over again. And so then with this cross-validation approach, we have 2 ways of comparing the performance of the model. One is, this is a very common method in classification approaches. Hold on just a moment. It's called, the area under the receiver operating characteristic curve. In this case, we're interested in predicting, is the well concentration of Gen X above or below that threshold of concern? And so this plot shows basically the false positive rate, the true positive rate is a function of false positive rate. So our ideal, of course, is to have a perfect model that doesn't give us any false positives and identifies every single well that's at risk. And that would just be right up here. In real life, that just never happens. And then this curve would have an area of 1 because you just would be this L, and underneath this, you capture this whole area. In real life, these classifiers, you really never have a perfect model. You typically have to, if you want to get identify more of your cases at risk, you have to accept that you're going to have more false positives. And so this ROC curve is, again, a measure of that trade-off. Again, one thing you could do if you really wanted to be conservative, test everything, assume everything needs to be tested. And that's basically guaranteeing you're going to have that, that basically all of your wells that are not really at risk are going to be identified as positives because you're going to test them all. But at the same time, you're not going to miss anything. So this really indicates that trade-off. So there's another measure that's commonly used. It's called the F1 score, and it gives you the trade-off between, kind of better idea of the trade-off between the possible trade-off between the true and false positive rate. So this would say, for example, how close can we get up to this corner right here? What kind of a trade-off do we need to accept? So just quick results. So this is Javad's initial model. Again, we started with 421 potential predictor variables and ended up with just 8. And they are in a circle starting here in terms of level of influence. And it turned out what was very interesting was that the most important factor influencing the Gen X concentration, that's right here. So this is our node where we're predicting Gen X, was actually the air deposition rate from the Chemours facility. This was not known at the time. It wasn't accounted for in the DEQ's initial groundwater models, and that's one of the reasons they weren't doing a good job and why we were seeing high concentrations in wells that were up gradient of the plant. And so once that's accounted for, then the predictions get a lot better. So that, and this was again backed up later on with measurements. So then what we did is we built this mechanistic model. Again, that was Rohit. And we said, well, what if we take this original Bayesian network model? This is Javad's model again, and it's in the center here. And we add some of the outputs from a mechanistic fate and transport model. Some of these outputs are fluxes in various directions. So that's what these are. Velocities, also a predicted Gen X concentration. So if we take all these and we add them, what do we get and how well do we predict? And so this is a comparison, kind of the bottom line. I'm going to say that a big limitation of this comparison work is that to produce a mechanistic model estimate of the concentration at a particular well, you have to know how deep the well is. And we didn't have that information from the original data set of 1,207 wells. And so Javad sent a survey to all 1,207 well owners and said, please tell us about your well. How deep is it? What's the construction method? And only 424 responded. A big advantage of Bayesian networks is we can still go ahead and train a Bayesian network even when some of the information is missing. They're able to leverage information from the non-missing observations to make predictions for wells with missing values, but you can't do that with a mechanistic model. So for our comparison, we're stuck with building a Bayesian network with a much smaller set of observations. And the bottom line is that if we look at the area under the receiver operating characteristic curve, again, comparing the true positive rate up here with the false positive rate, this ranges between 0 and 1. We want this curve to be shifted as far up to the left as possible. And this area is the area under this curve. And so the original Bayesian belief network, this area was about 0.85. These are different, the curves show different runs of cross-validation. The mechanistic model, our cross-validation there was the performance was just a little bit lower than the Bayesian network. And the combined did just a little bit better, 0.87. And this was statistically significant improvement. So the kind of order of accuracy was the combined model was a little bit better than the original Bayesian network, which was better than the mechanistic. If we look at the F1 score, it's the same logic. This is a little bit more confusing, but basically the F1 score kind of depends on your decision threshold. That is, you have to decide at what point are you going to go ahead and say that a well should be investigated. So for a mechanistic model, are you only going to investigate where your model says the concentration is 140 nanograms per liter or more? If you do that right here, you're going to have a very low F1 score. It's just about 0.45. You can do a little bit better if you say, well, we're going to not just investigate where the model says the prediction is above 140. We're also going to test those where the model predicts that the concentration is above about 40. We can do better. What's notable about the Bayesian network is it's just not only has a higher F1 score, which is better, but it's much more robust across decision thresholds. So this peak isn't really a good thing. We want a model that's more like this. It's robust. The combined one is the best, very, very robust across decision thresholds. So really at conclusion, the simple Bayesian network outperforms the mechanistic model. It's got a higher area under the receiver operating characteristic curve. It's more robust to the decision threshold. it can enable leveraging of the full data set. So I expect much better predictions, and we get much better predictions when we use all 1,207 wells. But for fairness, we only trained the model with 424 wells. The hybrid approach is a slight improvement, but one thing to note is the Bayesian network also runs instantly. Once you train it, it's work to train it. You have to really discover the relationships, and that's an iterative process. But once it's trained and you know what the key variables are, it just runs literally in an instant on a laptop. Whereas running the mechanistic model, according to Rohit, takes about a month. So again, this machine learned model does very well. I just wanted to definitely acknowledge Javad. He really led the first part of this, and then Dr. Hannah Long started working with me recently and took over where Javad left off to see to take on the comparison of the Bayesian network and the mechanistic model. Javad's work is published also a couple of years ago, 2021. Hannah's work is not yet published, but I hope will be in the coming year. And then if you want to know more, with another of my former postdocs, Runway Lee, we've done some more investigation of Bayesian networks for predicting groundwater PFAS concentrations around Minnesota, around the kind of original PFAS manufacturing facility in Minnesota. And I also just want to say, if you want to learn more, the software that I use to construct with Javad and Hannah, those fancier models, is called Bayesian. It's kind of like a Cadillac compared to Netica. If Netica is like a bicycle, then Bayesian is the Cadillac, or maybe the Ferrari, if you're a car person. And but it's not free. There's also a really fantastic textbook called Probabilistic Graphical Models by Daphne Kohler and Nur Friedman. And so, I've spent some time reading through sections of that. If you really like probability theory, then that's a good reference. And I guess with that, I will stop and see if there are any questions.
All right. Thank you, Jackie. That's a great presentation. I appreciate that you put some background information there to explain about Bayesian model. That's make it really easy to understand. Thank you.
Mm-hmm. And I see there's one question about the papers. Yeah.
Yes, there's one question about ask to reshare the paper. I think I guess I can follow up with you.
Yes, I can. I'm happy to send all of my Bayesian network papers to you.
Yeah, I will follow up with you and then distribute with our colleagues. Right. I think I would like to ask a question. I started a question since I'm a host. I'll take this advantage.
Yeah.
So my question for you is that when I look at the Bayesian model, when you initially to describe the structure mechanism, right? Look like the binary, like for each input or each nodes, looks like the binary inputs, for example, the gas, low gas, or have gas. Or is that always the case, or you can have multiple inputs? So for example, medium gas, high gas, or low gas, some very basic questions.
Yes, that's right. Yeah, no, you can have multiple states. I was just showing you a really simple one. So even in the Ebola one, some of the variables had many, many possible states. A limitation, except in certain circumstances, you have to discretize continuous variables. And of course, the decision of discretize them, where you kind of, how you divide a continuous variable into bins of discrete values, that can also affect the model accuracy. And what some of my work that I showed at the end I didn't talk about it at all, but 2 recent papers have explored the influence of those kinds of choices on the accuracy of the Bayesian network. But there are certain cases where, depending on the nature of the conditional probability relationships amongst the variables, you don't need to discretize continuous variables.
Thank you. That's very helpful. So, Carol, you have a question. So Carol asked a question about, Carol, would you like to ask here? Or
Sure. It was very interesting how your work identified that a primary component of the high concentrations was the point of the air source. And I'm just curious, what happened? Was there any regulatory action or any sort of controls put in after this finding came out?
Yes, there was actually. The Chemours was ordered by the North Carolina Department of Environmental Quality to put scrubbers on. Also to stop discharging their wastewater to the Cape Fear River. And that led to an immediate drop, those two things, in levels in the Cape Fear River. So yeah, in that way, it's very much of a success story that the surface water really responded. Unfortunately, now there's a long legacy of contamination that's going to be around in the groundwater
Yeah.
for quite some time.
Thank you very much.
Mhm.
I think Graham has his hand up.
Excuse me. Okay. Oh, all right. Sorry. Yeah, Graham, please go ahead.
Thank you. Jacqueline, a wonderful presentation. I'm always proud to show my ignorance. This principle that the Bayesian influence can only be one way.
Oh, no, it's two-way.
Yeah, well, that's what was interesting me about the explanation of the model. It seems that a loop might allow a system to learn and come up to an answer in an unsupervised manner that's very useful. And I guess the corollary question is, are you making an assumption that they don't cycle that might not be true?
So that's a good question. So because of the mathematics of Bayesian networks, in the final model structure, you can't have cycles. The algorithms that learn those structures, for example, in an unsupervised algorithm, test every single possible arrow direction, or not, every one, but run through many, many iterations to find the combination of arrow directions that leads again to the lowest minimum description length score. The reason that not having cycles can be a bad thing for us as environmental engineers, of course, is, again, we have many dynamic processes, but there are now dynamic Bayesian networks. There's methods for building dynamic Bayesian networks. And the way that cycles are handled, for example, one of cycle we have to think about is time, temporal relationships. In that case, each sort of time is discretized into slices, just like when we build a groundwater model, we're discretizing the subsurface, and if we want time involved, we also have to have discrete time elements. And then each time chunk is a layer. And so its own Bayesian network that then feeds into the next time. So there is now methods for doing that. And it's one thing, if I weren't department head, I would really like to go back to school and learn how to do that. But yeah, down the road. And that again, the mathematics for that were really developed within the last 20 years or so, and are now available in Bayesian software. But yeah, that's kind of a new advancement.
All right. We have one more question, given the time and respect everybody's time. Paul, please go ahead.
Hi, yeah, thanks for that's a terrific presentation. So early on, with talking about the PFAS contamination, you brought up the point that high areas were adjacent to low areas, and that so you wanted to find out what would make that possible. Is it it wouldn't seem that air distribution would address that question. So were there other things that address that question, or am I wrong about air distribution addressing the question of high areas being adjacent to low areas?
Yeah, that's a really good question. So actually, I think I also failed to mention early on that one of the issues was that, again, high levels were being observed in wells that were substantially up gradient of the factory, where they wouldn't have expected to see any. So that's really where the air deposition comes in. And then other variables that were important in the network explain that kind of more local heterogeneity in the observations. Some of the other things that were important were like the soil bulk density, the soil pH, soil organic carbon, obviously the depth of the well.
Mhm. Okay, thank you.
Mhm.
All right. Thank you very much.